this webinar. In today's webinar, we're going to present our work on the Stride F4 project. In this project, we're trying to build a near crash diagnosing system to identify near crash events by analyzing the basic safety messages generated in the connected vehicle environment for individual drivers. Our system contains two major modules. One is the driving anomaly detecting module to identify the drivers whose driving behavior is abnormal, compared to his or her past normal driving pattern. And the other module is the conflict identification module. If both modules, return positive answers, a crash warning signal will be generated and alert the involving drivers. So this gives our audience a big picture of what our project is. Now I will let my student, Di Wu, to present the details. She's the person who did all the real work of this project. Now I want to hand it over to Di. Di, you can get started.
Okay. Hello, everyone. Thank you for joining this webinar. And okay, sorry, Di, let me interrupt you. This is the team of this project. Myself, Shuang Tu, I serve as the PI of this project. Dr. Robert Whelan served as the co-PI of this project. And Di Wu is our Ph.D. candidate. She's working, she's doing the real work. So she knows every detail of this project. And this slide is about the entire Stride team, the participating institutions across the Southeast region of this country. Okay. And okay, I think, yeah, Di, go ahead to start the presentation. So this project is about traffic safety. In our days, we have many safety alerts, such as the Amber Alert, Tornado Alert. But what about abnormal driver alert? Alert that can watch you for the danger when you are driving. With that, when a dangerous vehicle is coming toward you, you can get a warning message saying, watch out, there's a crazy guy coming close. And this is warning alert tool is what our project is about. So first, let's look at the background, the big picture. All of us know that the future of transportation is full automation. However, the full automation is still a long way to come. And the critical obstacle for full automation is safety. The good news is that the Connected Vehicle program can have significant improvement to the safety in a fundamental way, which has the tremendous safety potential. Next slide, please. The connected vehicle are vehicles that are equipped with onboard devices. They generate basic safety messages, the BSMs, and exchange the BSMs with the roadside units and the CVs. In the picture, the red arrow represents the roadside units communication, and the purple one means the V2V communication. The table here is the content of each BSM. The table lists the major attributes, including time steps, latitude, longitude, elevation, speed, acceleration, accelerations in X, Y, Z axles, and the BSMs are generated in the frequency of 10 BSMs per second. of each vehicle. Next slide, please. A little background of driver behavior. The literature shows that the driving behavior is the most important accident causation factor. As shown in the picture, a researcher found that the human factor present in more than in 93% of the studied crashes. And another finding is that the driving behavior differs significantly among individuals, and each driver has his or her own driving pattern. Next slide. As we know, driving is a system, and the driving system is composed of drivers, vehicles, roads, controls, and environments. And a crash is a result of a series of malfunctions of the driving components. And in this picture, the research of a dynamic of crash causation shows that the psychological procession of abnormal status already exists before the crash scene. So it is possible to identify the abnormal status of the driver before the crash scene. Next slide, please. Background on traffic safety. Let's have a look at the state of traffic safety engineering and studies. Nowadays, the transportation system is evolving towards the intelligent transportation system, the ITS, and the connected vehicle, and connected and automated vehicle, sorry. And the traditional safety studies methods are relied on the statistical models can no longer fit the role of the mainstream method. Researchers also show that the driving anomaly can be traced by the vehicle's trajectories, which are embedded in the BSM generated on the CVs. Although the advanced driver assistance systems has significantly improved the traffic safety, there still has rooms for improvement. For example, they rely on the information collected on the sensors installed on the Eagle vehicles. So when the sensors have some malfunction, then the ADAS will also have malfunction. So we need another tool using information from another channel, which is not relied on the Eagle sensors. For example, for the BSMs from the CVs nearby. And another thing is, if relying too much on the Eagle sensor information, which are collected on the scene, then the time to perform the chain of actions of crash evasion from will be not long enough. Next. So all these backgrounds motivated us to build an automatic safety diagnosis system in a connected vehicle environment. The purpose of this project is to develop a safety warning tool that can generate not from the can generate information warning not from the information from the vehicle itself, but from the environment. And it should be based on the most important accident causation factor, which is the human driving status. To break down the project, the research task has the following. One is to build a driving anomaly detection model, the DAD, that can determine if the driver is in abnormal driving status using only BSM data. The next is to explore what information needed in the BSMs need to be stored, how to extract them, and how to process them. Because this is a big data, it is impossible to store all the BSMs from the vehicles. And the third is to build a conflict identification model, which is the CIM, to identify the the conflicts using only BSMs, but it's the real-time BSM. Next slide. The reason for this breakdown was because we redefined the near crash. A near crash is a crash situation that is not yet a crash, but close to. But how close is close enough has to be near crash, does not have a legitimate definition. So here we define our near crash according to our need. And here's the definition. A near crash is a crash situation that satisfies both of the following two conditions. One is a conflict is present, and the other is at least one of the drivers who is involved in the conflict is in abnormal driving status. Next. So here's the conceptual architecture of the project. As we already know, the CV environment, BSMs are generated in the vehicles and exchanged between the vehicles and the roadside units. So in our project, we set up a cloud to collect the historical BSMs for a certain period of time. So using the historical BSMs, we train the model to generate thresholds to differentiate abnormal and normal driving status. The thresholds will be sent back to the vehicles on the road to identify abnormal driving status in real time, as shown in the blue directional arrows in the picture. You may have a question here. Why we put the DAD in the cloud instead of in the vehicle computer? The answer is for energy saving. The technique of offloading the applications from the vehicles to the clouds can significantly save energy for the electrical vehicles. And this is in line with the future of intelligent transportation system, the ITS. The future of ITS will have a multi-layer architecture, which is composed of 3 levels. One is the vehicle ad hoc network, which is built up by the CV BSMs. The level 2 is the edge cloud. And then the level 3 is a top cloud, the core cloud. And research has shown that application offloading can extend the battery life and give energy savings up to 45% to the electrical vehicles. Energy saving is a fundamental task, not just for ITS, but also for the human environmental sustainability. And here is the project overview. The purple is the cloud, represent our cloud. And in here, the cloud, we have the IO system and MySQL database and the DAD model to calculate the thresholds using the historical BSMs. And the system will keep a list of all the abnormal CVs, the IDs, and the thresholds. And the thresholds and the list will be sent to the CVs constantly. And in our CV, there's a in each CV there's a in-vehicle subsystem that contains the CNN model and part of the DADs. Next slide. And this flowchart shows our in-vehicle subsystem. The in-vehicle subsystem, in-vehicle computer checks its own driving status against the thresholds and check all the received BSMs to see if it is on the sender is in abnormal driving status or is on the list. So if any abnormal vehicle is identified, then the in-vehicle computer will check for the conflict Then if it's between, if the conflict is identified, then a near crash warning will be generated. So in summary, our whole system has two modules. One is DAD in the cloud, and the other is the CIM, which is in all the CVs. Next. So we'll introduce how our model is built in detail. And in order to build the DAD, first of all, we need to know what is driving anomaly and what is DID. First, from the common sense, driving anomaly, or DA, it includes driving under influence, driving with distraction, aggressiveness, and drowsiness. So these no concentrating behavior are likely to cause crashes, and these are one definition of DA. The secondly, not complying to the majority of the driving maneuver is also considered not safe, because crash is a real event. So the majority of the average are considered normal. So if you are not driving in the same way as the average, then you are considered abnormal. From this DA, so from this, the DA can be identified as deviating from the statistical majority. The thirdly, as driving behavior differs substantially between individuals, and everyone has its own driving pattern, such as the way the hitting the gas and the brake pedals, the wheel steering, or the distance that if you're comfortable to follow another vehicle. So a driver can drive several years to have an accident. So not complying with own driving pattern is also considered abnormal. So according to the above definitions of DA, DADs can use the following methods accordingly. One is to monitor and analyze drivers' physical behavior, exhalation, facial or body movements using the in-vehicle alcohol sensors and cameras. The second is to use socio-economic data to categorize risk drivers, as most of the insurance company using this second method. The third is use the historical trajectory data to find the driving pattern and to check if the driver is driving with the same way and with his own pattern. So the third definition is what we're trying to use in our model. Next. This is the flowchart that shows our DAD model. Our DAD model has 5 modules. The first is data processing and selecting KPIs, is key performance indicators. And the second is to learn what is normal. The third is detecting outliers. The fourth is determining abnormal driving events. And the fifth is system updates. All of these modules except number 4 processed in the cloud. The number 4 are processed in the in-vehicle computer. Next. And here's the result of the threshold panel generated by the DAD of module 1, 2, 3. For each KPI, the values of normal behavior are determined. So here is the panel of data that we recommend to abstract or extract from the BSMs to store for a certain period of time. And this is just a part of the example of one sample driver. Next. For the DAD model, there are several parameters that need to be determined. We use the sensitivity analysis to find the appropriate values for these parameters. And next, and this is the evaluation. Our DAD model is an unsupervised abnormal driving detection model. And the evaluations on the unsupervised abnormal driving detection is a constant challenge. So in our model evaluation here, we use the measurement of average procession. And the model was evaluated. You can see from this chart, and it just it can satisfy our model assumption. So next. The CIM. You might wondering, since we already have the DAD, why we still need to introduce the CIM? The reason is that a crash is a real event. Even when the driver is under abnormal driving status, the chance of having a crash is still very low. So we don't want to issue too many false alarms. Therefore, we use the CIM to shrink down the number of warnings. As the CVs are constantly receiving the BSMs from the nearby CVs, it will check constantly the nearby CVs against the list of the identified abnormal drivers to see if it's risky driving. So the in-vehicle computer will run the CIM, and when at least one of the driver, including himself, we call it a driver vehicle unit or DUV pair. If any of them is in the abnormal driving status, then it will run the conflict identification model. And if the conflict of our is defined as a traffic situation, that when the actual distance between the DVU pair is less than or equal to the critical distance. The critical distance is calculated by the time to invade when with the maximum possible approaching speed. We'll explain in the next slides. So we calculate the critical distance using the speed distance profile. We call it SDP. The SDP here is the time-stamped sequences of coordinates and the speeds of the driver vehicle unit pair. So we categorize the four scenarios to analyze the SDP profile and implemented the math model and also the computational model accordingly. Next. And for the case study, for the CIM, we used a total of 23 crashes, in which the crashes, the drivers were reported under abnormal driving status, such as DUI, driving while under influence, and or text on the phone, or being too tired for long driving. The driving status information were provided by the SHARP2, is the Strategic Highway Research Program. And under under the principle of privacy protection, the coordinates of the trajectories of the 23 cases were revised to be relative to a certain point, and that was unpublished. And as the stationary object can be used to represent a normal DUV when the speed is 0. So we used a crash between abnormal driving status vehicle and the stationary object, because we don't have any case found to have the crash between two abnormal driving status because the limit of data. So from this chart and the time, we have the evaluation done, and we think that our model can identify conflict according to our assumption and projection. So here are some discussions. So before the model implementation, as our working data is time series data, we performed the standard time series data analysis, but no periodicity was identified. This is reasonable because the driving behavior is substantially complicated, and most of the time series data do not have periodicity anyway. So therefore, we conclude that the models for the time series data cannot apply to the BSMs. We implement the DAD model from the scratch instead of using the existing machine learning models. Next. And here is the records when we run the pairwise coordination tests, but we did not find any identifiable patterns from a sample data. Next. To model what is normal in the second module of our DAD, we use the interval-based normal distribution. And this is a test of the standard normal quantiles of longitudinal acceleration of a sample driver. And this shows that the data is not strictly normally distributed, but close to a normal distribution. So we have some limitations in this model. The first is they attempted to the behavior status to determine the behavior status through the footprint of the vehicle can be inaccurate. We use the method, but it's not so strictly proved, because this is very complicated behavior. We just use this for the engineering simplicity. We just want to provide a tool to catch the abnormal. If we catch the abnormal and prevent some crash, then we will think we have some improvements. The secondly is in scoring the outliers, we are not very clear of the relative impacts of different KPIs. This aspect needs further research, much more research, and a lot of data. Well, for now, our data is very limited. And thirdly, we did not run the auto tuning of the fifth module of the DAD because lack of data. And changing driving behaviors for a driver might need a longer time than 1 month data, but we only have the data for just 1 month. So we are going to upgrade this in data research. And for the future directions, for the DAD, the research on behavior studies through the footprints of the vehicle is still our target, although this is a very tough one. And the relative impacts of the different KPIs, still we need more research and more data. And the third is the auto tuning. And for the CIM, the abnormal driving studies deserve more attention than the of the ADAS, and more research needed to be paid to the abnormal driving studies. And the second is upgrading the model from the sequential processing to parallel processing, because the computation limitation. We are currently research on this topic. And the thirdly is to specify the vehicle type, vehicle length, acceleration rate, deceleration rate, and improve the CIM to be more sophisticated and can be have more functionalities. And the third big module is for the data path research, which is relating to the 3 tiers of architectures and the edge computing. And this is a very interesting topic that we're also trying to get involved with. And next slide, here's some part of our references. It's selected a very short one. So here's what I'm trying to present. Questions, please.
Okay, yeah, thank you, Dee. One thing I will, Dee forgot to mention is the source of the data we use. We bought the data from Virginia Tech Transportation Institute, and because of the limit in the budget, we bought only 30 days data. So probably that's the major limitation. Because if we have more money, we should buy longer period of data. Then that will make the analysis probably more convincing. That's that's what I want to supplement. And audience, while you are entering your questions in the chat window, okay, please answer the survey questions in the chat window. I believe I'm done. Provide a link here. Yeah. Okay. Yeah. Please answer the survey questions here. And okay, now the Q&A section.
Yes, we've had a couple of questions come in. First of all, we had one question about the recording of the webinar. We will provide a recording to everybody within the next couple of days, so you can get a video of it. We have a couple of questions about the content. The first question is, which variables were considered for the determination of abnormal driving status?
Okay. Dr. Tu, can you put the slides to, let me see. Number 16. Oh, sorry. Sorry for the acronyms. So this is the KPIs showed in this slide. Number 16, please. Is the DAD resulted panel.
Okay, great. Okay, our second question is, what is the time from BSM broadcast, time in cloud, time back to vehicle and driver alert?
Well, our plan is consistently all the time. When the thresholds are generated, it will broadcast to the edge computing, or without the edge computing directly to the vehicles. And the list will constantly update it. And the vehicles will receive from the infrastructure to vehicle, the BSMs. And our thinking is when the car or the vehicle is crunched, start running, it will download the panel table before it's hitting the road. So it will have the panel, although the panel should be very huge. But if we include the edge computing, that will solve the problem to a much manageable way. So this is the data plus problem. We recommend to do it constantly.
Okay, great. We have some more questions here. One of them is, how long does it need to observe, monitor the driver in the car to obtain a statistically reliable pattern of normal driving?
Well, we only have had 1 month data. So we're not very sure how long actually it needs, but I think it depends on the cloud, the capacity of the cloud, because in the future there will be huge amount of data. If the cloud is big enough, maybe you can store 1 month or 2 months or half a year to identify for the system updating. This is what the system updating is doing, is supposed to do. But we don't have the data, so we have not do the auto tuning. Again, it's need the capacity of the cloud, the computation, and also the collecting the data.
Okay, we had a question about how many drivers were involved in the 30 days worth of data that you collected, that you used.
I mean, in the DAD model, we first
how many sample participants were involved in the method development and testing? So you mentioned 30 days, and so they were curious how many drivers.
Well, for the DAD, we have we use the BSM data from Ann Arbor, the CV pilot study. It has more than 5,000 vehicles, testing vehicles.
Okay, great. Let's see. How to test if the warning generated by the method is accurate or not, an overcautious warning. So I think they're trying to know how you would test if the warning is an overcautious warning.
Well, we think the overcautious is okay, because there's it's just a trade-off of the cautions and the actual computation. We think at least we prevent the overcautious. So we did not put the focus to the overcautious. We just try to low down the overcautious by adding the CIM module.
Okay.
We need more data to do that. If we have. That is a very interesting topic.
Great. And we have one attendee who says that we have made available years of BSM data from the Wyoming CVP that you can use free of charge. And they also provided a link in the Q&A to Connected Vehicle Pilot Sandbox. So that's a great resource. Thank you for providing that.
Thank you.
We have another question. Would you please explain more about the collected data? The date, what kind of vehicles was it collected from, RSU or OBU?
Well, the data we use we just download from the pilot study data pool. They have all kinds of data, all kinds of vehicles, and I think the date is 2012 October. They did the pilot study in Ann Arbor, and the data is free online. You can download it for free. They have some very detailed explanation on the manual of the data.
Okay.
We cannot differentiate the data type or the vehicle type. Maybe later we should include that, but we don't have the capacity to do that now.
Okay, super. We have a question. Were driving conditions such as rain or fog considered in the sampling?
No, not yet. We have very limited samples, so we did not differentiate that yet. But it will be included in the future. If it's not me, somebody else should do that.
Great. Let's see. Okay, so here's a question. Since you are only looking at cases where there is change in driver behavior, your system is a less conservative system than a comparable system when you consider time to crash or a similar measure. In a safety-oriented study, we would like to be as conservative as possible to avoid possible crashes. Can you explain your logic behind your logic?
Oh, I need a
yeah, it's a bit longer.
The question again.
It's in the Q&A box, so you could pull it up and take a look.
Oh yes, I see it.
And if while Dee is getting a chance to read that, please take a chance to look at the chat box. There is a link to a survey, a very short couple question survey for today's webinar to help us plan for future webinars. And we also provided a link to our fall Stride webinar schedule where you can learn about upcoming webinars and register for any that you're interested in. So from there, I'll go back to the Q&A.
Okay. This is a very important question. We explained how conservative we can be in our paper for the CIM, because we use the maximum possible time to invade to calculate the critical distance. So we think we are very conservative in here because of the maximum speed we are using. How about I send you the papers so that you can read and we can discuss later.
Yes, we can. When we send out the recording, we'll provide a link to the project website, the web page on our Stride website, and that will be where the final report is posted. Wonderful. I don't think we have any additional questions. Do either of you have any additional comments or things that you'd like to add?
I'm good. Thank you.
Well, no, I want to thank the audience who attended this webinar, and as Andan mentioned that the more information will be available on the Stride website, so we will discuss, in more details if, you're interested. Yes, thank you very much.
Thank you very much for attending today, and we hope to see you on future STRIDE webinars. And thank you very much to both of our speakers today.
Thank you.
Thank you. Everybody has a nice day.
Thank you. Bye-bye.
Bye.
Bye-bye.